Hello everyone, my name is Daniel Maldonado Lopez. I am a material science and engineering PhD student at the Mendoza Group at Michigan State University. I am going to go through and explain how to send your first crystal calculation um, on the HPCC, which is the supercomputer at MSU. Um, okay, so let's get started. First of all, I wanted to show that we have a wiki page where we have a lot of information about these programs that we're going to use to run these quantum mechanical calculations. In particular, this webpage for Crystal 17 is the one where we're going to grab all the information for this particular submission. We will need two files in order to submit a calculation. Those two files are this one, submit.slurm, which you can just copy and paste into your HPCC directory, and this one, which is graphene.d12, which this is an input file for Crystal 17 in this case. Once we go ahead and copy and paste these two files into our folder in the HPCC, I will talk a little bit about these and show you what some basic information about these files and what they do and how to send a calculation. So I'm going to go to my terminal here. Something important about the HPCC, when you start out, you're going to start out and you're going to see a screen like this one. Here it indicates several development nodes, and you need to SSH into one of these development nodes in order to send a calculation. So we're going to go ahead and just pick one at random. We try to pick the ones that have lower usage, just as a rule of thumb. So we're going to do SSH, then copy and paste that the name of the developer node, and then enter. And now you will see that my user changed from Gateway 02 to Dev Intel 16, which means that we're now in a developer node. Now I'm going to move to the directory where I have my files. And right now I already ran this calculation, so I have a .out and a .f9. But you will first only have a graphene.d12 and submit.sbatch. So the first thing I'm gonna do is open up the D12 so we can talk a little bit about that. Okay, so this is exactly the same as we have in our wiki, and the input file for Crystal is divided into a few sections. So I'm going to broadly talk about this, and maybe in a future video I will talk about this more in detail. So first, this entire section is the geometry section. Here we define what type of structure we want, either 3D, so like a crystal, a slab, or like a 2D material, a 1D material, or a 0D material, and that depends on this keyword here. We also define the symmetry group, the lattice parameters in their simplest form, the number of atoms that we want for our unit cell, and the atomic number for each one of these atoms that we define here in the number, and its atomic positions. And here specifically we're doing a geometry optimization, full optimization, so lattice parameters and atomic positions. And we also define the maximum number of optimization cycles that we do. And then we end this geometry optimization block by doing end opt, and then this end closes this first entire block. That's the first block. The second block is from here. I will highlight it in a second. So from here all the way to here. So this entire part is another block, and this is the basis set part, or basis set block. And what we do here is essentially define, so Crystal 17 and Crystal 23, they use Gaussians as the way to describe atomic orbitals, and these numbers essentially describe the shape of the Gaussians that are used to describe the different atomic orbitals, in this case for carbon, because we are running a calculation for graphene. So the only atom that we have, or rather the only atom type that we have, is carbon. So we'll talk about these a little bit more in detail. One thing to note is that they always end in 99.0 end. So this 99.0 is needed always in these calculations in order to close this entire block. And the third and final block is the DFT block, or the SCF block, where we define if we want to do DFT or Hartree-Fock, the functional that we're going to use, the integral tolerance, the energy tolerance, stuff like shrinking factors, and number of cycles for the SCF procedure, and some other parameters that are important for the DFT calculation. And this is so it goes from here, from this, after this end for the basis set section, all the way to the end of the file. So those are the three main sections for an input file for Crystal. Now I'm going to go through and show you the SBatch file, which is our submission script for the HPCC, which is needed in order to allocate resources for a calculation. So let's go into that. So this is a very simple submission script. This first line determines the number of cores that we're going to use. In this case, it's only 4. This next one determines the number of nodes that we're going to use. In this case, we only need 1 node. And if you don't know what a node is just a collection of cores. And we will talk about it a little bit more in detail later. But that's essentially what it is. The memory that you need for each CPU, the time allocated for the calculation, in this case 7 days is the maximum that we have at the HPCC. We also define the partition where we want to run our job, and the job name and some other parameters. All of this is pretty standard for, in this case, Crystal 17, which is the program that we're going to use. All of this is left pretty much unchanged in every single calculation. The only thing that changes is the job name. So it's important that this job name here and this export job equals, they both have to have the same name, and it's the same name as our D12 without the D12 extension. So in this case we have graphene.d12, and we only need to define graphene in these parameters here. The other thing is to change the number of cores, number of nodes, and time accordingly, and the memory accordingly. And that's pretty much it. And now to submit your calculation, the command that we use is sbatch, and then we're going to submit the job script. So submit.sbatch. Once we do that, we will get this code, submitted batch job. And then if we use a command called QS, we can actually track how this calculation is going, if it's right now in queue or if it's already running, and so on. So in my case, I am going to cancel this with scancel and then copy paste the job ID, because I don't want this to run at the moment. I already have the output ready here. And once you run the calculation, you will see something like this. If we go to the very bottom of this calculation, we will see these lines, which indicate that the calculation was terminated successfully, and we will get a bunch of information about our system, such as the lattice parameters, the atomic positions, and so on, after doing a geometry optimization in this case. So that's pretty much it for your first Crystal submission. I believe in the next few videos we will be talking about properties, we will be talking about more into detail about the D12 and the formatting for that, and so on. So yeah.